Let's have a recap of what we covered till now. That we have covered the basic definitions associated with the topic of circular motion. Then we have discussed in detail about linear and angular displacement, velocity, acceleration, and their interrelations, how they are related. Then after that, what we covered was uniform circular motion and a non-uniform circular motion. And then under the topic of uniform circular motion, we discussed something about the time period and frequency. Today, we will be taking our topic to the next level to cover up the discussion of centripetal acceleration. So it's a centripetal acceleration. And once we come out of this, we will go ahead with centripetal force. And after that, we will discuss something about banking of road. So let's begin our today's topic with the discussion of centripetal acceleration. Now, in the introductory part itself, we discussed that to have a circular motion, what is most essential thing is to have a centripetal force, which is a force directed towards the center of that circular motion. So we will try to find out the needed formula, needed derivation for the centripetal acceleration and centripetal force. So let's consider an object which is performing a circular motion on this track with center somewhere here, the center of circular motion, and let's say that we have an arbitrary position of the particle here. Now we know that to have this centripetal, to have this circular motion, we definitely need velocity of this particle tangential at this position. So this must be the velocity of particle, and this is true for every location. Like suppose if we say that the next position after some time is at this point, then at that point also we know that velocity of the object at that point must be tangential at that point. And we discussed that in uniform circular motion, the speed is constant, but the velocities, they are changing. Like this velocity is v1 and this velocity is v2. Let us say that this is point A and this one is point B, such that velocity of object at point A is v1 and the velocity of the object at point B is v2. Now, let us analyze this situation in a vector algebra. For analysis part, we need to consider the 2 points to be very close to each other. That's what we discussed earlier also. So for explanation purpose only, we have drawn the point A and B at sufficiently large distance. But when we analyze it mathematically, we have got that restriction that we need to take limit delta t approaching to 0. This is an important consideration. Like we need to analyze the motion by considering the 2 points which are infinitesimally closest to each other, and then we analyze it. So this may be our point of analysis A, and this is the point B. And for explanation, for simplicity of explanation, we had taken this point like this. Okay, so now if we analyze this situation using the vector part, we can easily say that we do have one vector v1 which is in this direction, and the second vector v2 and v1, like, sorry, this is v2, and the second vector v1 like this. What we have done is we have just converted this complete circular motion part into the vector algebra. So this is our vector v2, and this is the vector v1, and this is, let us say, an angle d theta. Let's call this angle as d theta, which is a very small angle d theta, such that this part will be dv, means the difference between these two vectors. And it's quite clear. If you look into the vector algebra, we can easily find out that we can write down the equation v1 plus dv, which is a vector again. So this is also a vector, is equal to v2. That can be easily observed from this triangle, vector triangle. That's what we can write down. That's what we can write down, like v1 deferred with v2, or I will write down it in correct way, v2 minus v1, that is equal to dv, which is nothing but difference in vector, isn't it? So if we just analyze this situation with a consideration like d theta is infinitesimally small. That means that itself means that the point A and the point B, they are closest. Then we can write down an equation saying that sine of d theta is equal to dv divided by v. Sine of d theta, opposite side, divided by the hypotenuse, which can be any vector v1 or v2, we call that v. But then, since d theta is infinitesimally small, means very, very small, we can easily say that sine of very small angle can be written as the angle itself, which gives us the value like d theta is equal to dv divided by v. That's what is the angle d theta, and this is to be noted as equation number 1. So we can simply say that now this angle d theta is equal to dv divided by v. So this dv, change in velocity, can be written as v into d theta. Similarly, we can write down now dv by dt will be equal to v into d theta by dt, dividing both the sides by dt. But we know dv by dt is nothing but acceleration, and we know d theta by dt is nothing but angular velocity omega. So we get the equation acceleration is equal to v into omega. Now what's v? Linear velocity. What is omega? the angular velocity. To this equation, now if we substitute the values like v is equal to r omega, I can say that we get another variant for this acceleration, like if v is substituted as r omega, it becomes r omega square. Or to the same formula, to the same step, if we now substitute the value like omega equal to v divided by r, so I can get another variant like acceleration is equal to v square by r. And thus, we can summarize the formulae for centripetal acceleration like acceleration is equal to v omega, which can be written as r, which can be written as r omega square, or it can be written as v square divided by r. We can use this understanding to discuss about something called centripetal force. Now that we know that centripetal force, we know that the centripetal force will be equal to mass into the acceleration. Now, if we substitute the value of this acceleration, that's what we have derived in our earlier screen, we can get variant of this centripetal force like m v omega or m r omega square or m into v square by r. So we can use any one of these available variant to have a discussion of centripetal force, which is directed towards the center of the circular motion, and hence the centripetal acceleration, which has to be in the direction of force, that is also directed towards the center. So we can simply say that if this is the direction of centripetal force, this will be the direction of acceleration, which is exactly opposite to the direction of the radius vector. Hope this is clear to all. Now, having understood the concept of centripetal acceleration and centripetal force, we can easily find out the speed of an object that it must have to orbit the Earth under gravity. And that's what we call as orbiting speed. So let us consider the circular motion. Let's say that this is the Earth. This is Earth, which it's a center somewhere here. And let us say that this is the radius of Earth, which we represent with capital R. Now imagine an object which is on the surface of Earth. So this is experiencing, no doubt, the gravitational force, which is in the direction towards the center of Earth. And if it wants to orbit around the Earth, then the same gravitational pull works like centripetal force. So we can simply say that the gravitational pull is providing us the centripetal force. And now we can say that it's a simple like mg, where m is the mass of the object, g is the acceleration due to gravity. Same here is m, which is mass of object, and then we can substitute the value of acceleration v square by r. So I can simply say that with this, we can find out that the orbiting speed can be calculated as the root of rg, which gives us a direct hint that the orbiting speed is directly proportional to the square root of radius and the acceleration due to gravity. To which, if we substitute the values for radius of Earth, I think we should have substituted it with capital R. We can get the value like R, which is the radius of Earth. It's a standard, which is 6400 kilometers. And acceleration due to gravity, if we substitute the value of 9.81 meters per second, we get like 6400 into 10 to the power 3 into 9.81. And if we just find out its numerical value, its value somewhere come close to 7.92 into 10 to the power 3 meters per second. And that gives the orbiting speed for an object on the surface of Earth. The same concept can be applied to the orbiting speed of an object which is taking its motion on, let's say, the curved surface. Let us say that this represents the road from the top view. It's the eagle eye view where we are looking onto the geographical structure from the top. So let's say that this is the curved road on which we find out that this is the vehicle which is intended to take its motion like this. This is the intended motion of this object, which is vehicle. So naturally, if we just logically complete this track, there will be center of this circular path somewhere here, and we can easily say that with this intended path, there can be the radius r for this circular motion. If m is the mass of this vehicle and if r is the radius of this circular motion, we can still apply the equation which we have derived earlier to find out the possible maximum velocity to be calculated as root of rg. So if I want to increase the value of this allowable velocity, the allowed velocity for this vehicle, there are two ways. First, increase the radius of curvature of this road, means instead of having a more curved road, we should have a more flat road. The radius will be larger. Or we have to increase the acceleration due to gravity, which is absolutely not possible. So we do not have any control on the parameter g. So one of the possible solution to have a higher value of this allowed velocity is that instead of constructing a curved road, try to build the straight road. But that's not every time possible. There are many situations where we find out that we need to go for the curved road. Under that situation, to allow to go for the higher velocity, we have got one more solution, and that is called the banking of road. Now, banking of road is as simple as we can say that it's raising the outer surface, of road over the inner surface. Means, suppose if we look into the same situation, but from a vehicle which is behind it. If we just look into the same situation, but from the vehicle behind it, the situation will appear to us like this is the road, this is the road surface, and on that road surface, we are going to observe the vehicle. This vehicle like this. We are looking from behind. So the same scenario will appear like this. Now this road is the normal road. Banking of road says that raising the outer surface of the road over the inner surface means instead of making that vehicle to travel on a road which is flat, what we do is that we raise the outer surface of the road over the inner surface by, let us say, some angle theta. This type of raising the outer surface of the road, this surface, the outer surface of the road over the inner surface, this is called banking of road. And now on to that, the vehicle can take a turn with a greater velocity than this one because of this banking. Let's see how it happens. Now, we know that when the situation was like this, the weight mg of this particular object was acting vertically downward. This was the weight mg, which was correctly balanced by the normal reaction from the surface we call as n. But in this case, the weight mg is still very much acting vertically downwards. No doubt onto that. But this time, it is not balanced correctly by the normal reaction, but one of its component. So if we draw first the normal reaction will be, just 1 minute, the normal reaction will be in this direction. It will be in this direction. So now we cannot write down the equation which we could have easily written here, that normal reaction is balanced by mg. Here it is not the situation. Here the weight mg is balanced by one of the component of this normal reaction n, and that component is n cos theta. So we get our first equation like n cos theta is equal to mg. Now, what about n sine theta? So n sine theta, which is in this direction, this n sine theta takes care for the centripetal force. So we can easily write down this part as n sine theta is equal to mv square by r, where r is the radius of curvature of that road. So if I call this as equation number 1, and if I call this as equation number 2, and then somehow we say that equation number 2 divided by equation number 1. If we perform this operation, we can easily find out that this becomes n sine theta divided by n cos theta will be equal to mv square by r divided by mg. Doing the mathematical processes like cancelling out the common, we can easily say that we get an equation which is tan theta is equal to V square divided by RG. Or we can simply write down V square is equal to, or let's erase this off, directly going for velocity term, or V is equal to root of RG into tan theta. Now, what's the advantage of this is that if we do not change the radius of curvature, we definitely cannot change the acceleration due to gravity. But instead of making that road as a flat, if the road is banked at an angle theta, now this theta governs the equation. Like we know, if theta increases, tan theta also increase. So if we increase this value of theta, tan theta increases. Result of that, velocity value also increase. And this value will be much more greater than the value which we have discussed here. This is the value, this is the allowed value of velocity when the road is flat. And this is the allowed maximum velocity when the road is banked. Now it depends upon angle of banking. You increase the angle of this banking, we will find out that the allowed velocity value also go on increasing. In a very special case, suppose if we say that theta becomes 90 degrees. Now, if theta becomes 90 degrees, which is infinity, so the allowed value becomes infinity. And that's what exactly happens in a situation like the well of death, where we know the speed with which those bikers they run on the walls of that well has got extremely high velocity. But that's then a very exceptional and a very special case. Looking into the practicality, wherever we need to construct the roads with a certain amount of curvature, if it is constructed like this, which is a normal flat road, we get some value with which we get some maximum value of velocity with which the vehicle can go without any problem. Suppose if we want to increase that velocity, then the simple solution is to go for banking of road. Just bank the road with an angle theta without changing the radius of curvature. We can still increase the possible value of this maximum velocity. And that's what we call as the banking of road. Hope this is clear to all.